In this short video, I'm going to recap the concept of the mole and molarity and give some worked examples that demonstrate how to perform calculations that convert between masses and moles and determine the molar concentrations of solutions. Chemists are interested in understanding the world at the atomic and molecular level. We make our observations on the macroscopic scale using quantities of substances that we can weigh and measure, but what we're interested in working out is how one molecule interacts with another on the atomic scale. As you will see, the concept of the mole allows us to bridge from that molecular level to the macroscopic scale in which we make our observations. And that allows us to work out the number of molecules that interact with each other. There are going to be some big numbers involved here in changing the scale. If we look at a teaspoon of water, it has a volume of about 5 milliliters. And even though this volume is quite small, as you can see on this teaspoon here, it still contains a huge number of water molecules, 1.67 times 10 to the 23 molecules in fact. Similarly, here we see a small mound of glucose powder, which has a mass of 18 grams. But even though this small mass of glucose, it still contains 6.0 times 10 to the 22 molecules of glucose. Using numbers of this size would be overly complex in our calculations. So to help us to count atoms and molecules, we use the mole concept to bring these enormous numbers down to a more reasonable scale that's much easier for us to handle. Let's use glucose as an example molecule to demonstrate how this works. If we look at the glucose molecule itself, we can see that it's made up of 3 different elements: carbon, hydrogen and oxygen. We find that one molecule of glucose has the chemical formula of C6H12O6. This of course means that it's composed of 6 carbon atoms, 12 hydrogen atoms and 6 oxygen atoms. To help us count the number of glucose molecules, we need to know its mass, and we can work that out by looking them up, these individual masses of each of the atoms, from the periodic table, and then we can sum all those masses to find out the overall mass of one molecule of glucose. So here we are, here's the periodic table, and what we're going to do is select each of the atoms in turn. Carbon has an atomic mass of 12.01 atomic mass units. Here we can find hydrogen, and it has a mass of 1.01 atomic mass units. And finally, here's oxygen, and it has a mass of 16 atomic mass units. What we do next is multiply each one of these by the respective numbers of each type of atom in our glucose molecule, and this gives us the following. We've got 6 carbon atoms, each having an atomic mass of 12.01. So 6 times 12.01 gives us 72.06 atomic mass units. We have 12 hydrogen atoms, each having an atomic mass of 1.01. So 12 times 1.01 gives us 12.12 atomic mass units. Here we have 6 oxygen atoms, each having an atomic mass of 16 atomic mass units. So 6 times 16 is 96 atomic mass units. Finally, we add all these up and sum the masses to give the formula mass of one molecule of glucose, which is 180.18 atomic mass units. Now this is the mass of one molecule of glucose on the atomic mass scale, which we simply cannot weigh out. However, if we add more and more and more glucose molecules, we get to a point where we go from the atomic scale to the laboratory real-world scale, and we can actually weigh the amount of glucose. If you look at this mass of glucose here, we can see that this number is 6.022 times 10 to the 23. This number allows us to scale up from the molecular level to the real world level. This number, 6.022 times 10 to the 23, is known as Avogadros number, and we use it to define the mole. This number of anything is known as a mole of that thing. So we have 6.022 times 10 to the 23 glucose molecules, which is a mole of glucose molecules. But if we had 6.022 times 10 to the 23 bananas, then this would be a mole of bananas, and that's a lot of bananas. Now the key to how this works is the mass of the mole of the substance. As you can see, if we have 6.022 times 10 to the 23 molecules of glucose, or 1 mole of glucose, this has a mass of 180.18 grams. Now notice that we've seen this number before. It's the same value as the mass of 1 molecule of glucose in atomic mass units. Therefore, the value of the mass of any substance in atomic mass units is numerically equal to the mass of 1 mole of that substance in grams. In our example, glucose has a molar mass of 180.18 grams per mole, which means that every 1 mole of glucose, or every 6.022 times 10 to the 23 molecules of glucose, have a mass of 180.18 grams. Now, knowing this molar mass allows chemists to work out how much of any substance they're dealing with and how many molecules or atoms they are having in their reactions. We can use the following equation to help us. The number of moles is equal to the mass of the substance divided by the molar mass. Remember, we can calculate the molar mass of any substance if we know the chemical formula of that substance and we look up the atomic masses of the elements from the periodic table, just as we did for glucose. As an example of how we can use this equation, we're going to determine the number of moles we have for a particular mass of glucose. We would like to know the moles present in 36 grams of glucose. From our previous work, we know that the molar mass of glucose is 180.18 grams per mole. Again, remember that this means that 1 mole of glucose has a mass of 180.18 grams. So in our example, we have 36 grams, which if we think about it, is less than 180.18 grams, so that we expect our answer to be less than 1 mole, a fraction of a mole. Using our equation, we can input our values as follows. The number of moles equals mass of our substance, which is 36 grams, divided by the molar mass, which is 180.18 grams. And this gives us the answer of 0.199 moles. So a mass of 36 grams of glucose is equivalent to 0.199 moles of glucose. In our second example, we're going to use our equation to determine the mass of glucose from a known number of moles. We're essentially going to do the reverse. Here we have been given the number of moles of glucose, 0.8 moles, and have been asked to say or work out the mass that represents. To help us, again, we're going to need our molar mass of glucose, which we calculated from the periodic table. But before we can use the same equation, we need to rearrange it first to solve it for the mass of substance. And we can do this by multiplying the molar mass by the number of moles as shown here. Our equation therefore becomes mass in grams is equal to the number of moles multiplied by the molar mass. So in our example, this becomes mass in grams is equal to 0.8 moles of glucose multiplied by the molar mass of glucose, which is 180.18 grams per mole, which gives us the mass in grams of 144.14 grams. So 0.8 moles of glucose has a mass of 144.14 grams. Now, working with solid substances is straightforward. We can see them, we can weigh substances, and we can convert masses into moles using our masses in grams and our molar masses. However, knowing how much of a substance is present in a solution, especially when our substance has been dissolved in the solvent, is not so easy. As you can see here, I've got 36.04 grams of glucose that I'm adding to 250 millilitres of water in a glass. As I add the glucose, so it dissolves and disappears. I can no longer obviously weigh the glucose. Instead, I need to express the amount of glucose dissolved in the water as a concentration. Now, there are several ways of expressing concentration, but here we're going to use molarity. By convention, we define molarity as the number of moles per litre, or the number of moles per decimeter cubed of solution. Now notice that the units of 1 litre and 1 decimeter cubed are equivalent. I would tend to use litres here, as this is what you will more commonly encounter when working in the laboratory. Now, the equation which describes molarity is shown as being equal to the number of moles of a substance divided by the volume of solution in litres. This gives us the molarity of solution, which is also expressed as capital M or molar. Yep. So when you see this big M, it means molarity. Now, in order for us to calculate the concentration, for any solid substance that we dissolve in our solution, we will need to know the number of moles it represents first. So for example, my 36.04 grams of glucose, I'll need to use my previous equation to work out the number of moles by dividing that mass by the molar mass of glucose to work out that I've got 0.2 moles of glucose. The volume of water that I'm dissolving this in is 250 millilitres, or in litres, this is 0.25 litres. I need to make sure again that I'm using the correct units. Using our equation, the molarity of our solution is 0.2 moles divided by 0.25 litres, and this gives us the answer of 0.8 molar, 0.8 m. Remember, the capital M is the symbol for molarity, and this means the number of moles in 1 litre, or the number of moles in every 1,000 millilitres. For here, this means that the concentration of our solution is 0.8 moles per litre, i.e. we have 0.8 moles in every 1 litre or every 1,000 millilitres of solution. So, for example, we know that a 2 molar solution of glucose contains 2 moles in every litre, or 2 moles in every 1,000 millilitres. But how many moles of glucose are there in 400 mils? So, again, we can use our equation to help us calculate this. First of all, we need to remember that the big M, or molarity, means that the number of moles in 1 litre, or the number of moles in every 1,000 millilitres. We have been given a 2 molar solution, so we know that there are 2 moles of glucose in every 1 litre, 2 moles of glucose in every 1,000 millilitres. So we take our molarity equation, and this time we rearrange it to solve for moles of solute, because that's what we want to know. We know the volume, we know the molarity, but we don't know how many moles this represents in that volume. So we do this by multiplying the molarity of the solution by the volume we are interested in. So moles of solute are equal to the molarity multiplied by the volume in litres, which is 2 molar, multiplied by 400 millilitres, which in litres becomes 0.4 L. And as you can see, this gives us 0.8 moles. So this means that if you have a 2 molar solution of glucose, there are 0.8 moles of glucose dissolved in every 400 millilitres, or every 0.4 litre. The key to molarity is to remember that it tells you the numbers of moles dissolved in 1 litre of solution. Once you know this, you can work out the number of moles on any volume that you've been given. Right, so to sum up, a mole of any substance is defined as having 6.022 times 10 to the 23 units of that substance. Remember, you can have a mole of glucose molecules, a mole of carbon atoms, a mole of Peugeots, whatever. The formula mass of any substance in atomic mass units is equal to the mass of 1 mole of that substance in grams. To relate masses and moles of substances, you need to know the molar mass of the substance you are interested in, and you can calculate that from the periodic table. Okay? To express the number of moles you have in solution, we use molarity. It's a way of expressing the concentration, and we define that as the number of moles of a substance dissolved in a litre of solution. Again, you can calculate the molarity by dividing the number of moles of a substance by the volume in litres that's been dissolved in. You can find out more about molarity, and there's more exercises and questions available from these chapters in these textbooks. All good chemistry textbooks, of course, will contain this information. And there are many more examples of questions and problems available on the internet, of course. You may also be interested to know that the definition of what is a mole is still being discussed and updated by chemists. And this interesting article from the Royal Society of Chemistry describes some of the more recent thinking on this subject.